I'm going to talk to you today about reflection modeling of black hole binaries, and I'm going to present two key elements that have come out of our modeling in recent years, two aspects of that that are quite key, which is returning radiation and the importance of the accretion disk density in these types of models, which is something that Agatha was discussing earlier in her talk. I just wanted to bring up briefly before I get into the details of that the recent detection detections of black hole mergers by gravitational waves by LIGO is sort of bringing into question now some of our, in particular, spin constraints on electromagnetically studied galactic black holes, for example. And I think this is quite interesting that these LIGO sources are either probing a different population of sources that are forming through a different channel, or it's calling into question a little bit our spin estimates that are skewed quite heavily towards very high spins, and trying to explain spins that we're getting for these sources is in some cases a little bit of a challenge. And there has been some questioning of our modeling techniques or whether or not we can really get a non-degenerate constraint on spin. And I think there's some validity to that. So in the case of black hole X-ray binaries, there are so many things, despite all the rich data sets we have available to us and all the phenomenology we observe and the types of modeling we can perform on spectral characteristics as well as timing characteristics of these sources. We still don't understand, for example, jet launching. We don't have a good handle on the geometry of the corona. We don't have an agreement about the degree of truncation of the disk in the hard state, for example. And these are all key things for constraining something like the spin of the black hole. There is not a completely non-degenerate way of constraining that. And in recent years, we've been trying to make use of the RXTE archive, of course, as Jeroen mentioned in his talk on NICER. There's a lot of data available there, of course, not at beautifully high spectral resolution, but nonetheless, data that we can make use of. And we've been applying reflection models to and studying various aspects of these sources, but mainly trying to trace how the accretion flow behaves as the source is going through its outburst. And I'm going to show some results that come from modeling of these two sources, XTE J1550 and 4U1630. I'm going to start just by explaining, when we're applying reflection models to these sources and modeling the continuum emission as well, this is typically what we're seeing, mostly in this case, in the hard state of, for example, GX339-4, where you have this disk emission in the soft band and coronal emission in the hard band, and obviously dominating to varying degrees depending on the spectral state. And then the coronal emission, typically we're seeing that the fits to the data imply that the coronal emission is illuminating the accretion disk and giving rise to, in most cases, both a relativistically broadened reflection component and actually a narrow light component. And that's something that Jeroen discussed also in his talk a little bit. And it's the relativistic component that's smeared by the proximity of the disk to the black hole. This is the part that allows us to get some constraints on either the geometry of the system or the spin of the black hole, given that the proximity depends on spin. It appears my slides are not moving forward anymore. Okay, figured it out. So I'm going to show one key result that came out of modeling of this source, XTE J1550. Please, I encourage you to go and check out the paper we published last year, because there's a few things that came out of modeling of this source that I'm not going to discuss in any detail. But essentially, we modeled the continuum and reflection components as the source goes from the hard to the soft state in two different outbursts and tried to compare the accretion flow properties there. But one of the main things that we found that was interesting to us is when attempting to model the reflection spectrum during the soft state of this source, we found, as shown on the left-hand side here, that simply throwing a reflection model that assumes the coronal emission is dominating the radiation of the disk and producing the reflection doesn't work very well. And the reason for this is actually relatively simple when you think about it. The spectrum is highly dominated by the disk with only a few percent of the observed flux in the corona. And when you try to model out the line features in this source with any reflection model that has a very wide parameter space, you can't get a good fit to the data without having this dominance of the Compton hump component at high energy. So that's shown with the red line there in the left-hand figure. What's interesting is we tried, in this case, assuming, well, maybe the illuminating continuum of the disk is not actually a power law, it's more like a black body. When you do this, you find that you can fit the line features of the data very well, and the edge, the ion K edge. without this dominance of the Compton hump that allows you to get a realistic overall fit to the data where the Comptonized component is fitting out the high energies. And this is simply because you don't have so much high energy radiation in the irradiating continuum as you do with the power law, which would naturally produce a strong Compton hump. And energetically, this makes some sense. There's only sort of on the order of 5% of the flux in this black body reflection component shown on with the red line on the right-hand side here, which is somewhat expected that if you simply do the ray tracing calculations, that something on the order of 5% of the photons for this source should be returning to the disk. So essentially what I'm saying is what we think we're seeing here is returning radiation. So this could be photons originating from the inner part of the accretion disk and being bent back towards the disk and producing reflection features. This prediction has been around for a while, and there are various papers exploring different elements of this that I won't get into. But there's also some recent work looking instead at the second order reflection, so returning radiation that comes from reflected emission being bent back towards the disk. There was a paper by Dan Wilkins last year, and Thomas Dowse is going to discuss this in his talk tomorrow. So I really encourage you to pay attention to that because it's really cool, the implications that come out of that. But this is, in our case, the fact that we think we're seeing the disk emission return to the disk and be reflected means that aside from continuum modeling, which is one way to constrain the spin in the soft state, we have perhaps here a slightly less degenerate way of performing reflection modeling, since we understand a little bit better what the accretion flow is like during the soft state, as opposed to the uncertainty on the geometry of the system during the hard state. So this could be another way of measuring spin. And I want to move on now to discussing a little bit the density of the accretion disk in reflection models and the importance of that parameter. So in decades past, reflection models have assumed usually a density of the accretion disk that's quite low, 10 to the 15 per centimeter cube, which is perhaps more appropriate for AGN, and that's something that Agatha was discussing earlier. But in the case of black hole binaries, that's not true. The disk of the density of the accretion disk should scale inversely with the mass of the compact object, and in this case, low mass sources. For any parameters that you play around with, as shown in the top left figure here, the density of the disk should be fairly high, beyond 10 to the 20. And reflection models have now been developed to include the effects of increasing the density to this value, to these sorts of ranges. The ionization of the disk, of course, depends on the irradiating flux of the disk and the density. So this is very key for how the reflection spectrum will appear. It's a very strong function of ionization. And one of the key things that comes out of this is, as shown by Javier Garcia in 2016, is as you increase the density of the disk, you get a lot more heating in the upper atmosphere of the flow. And this will produce quasi-thermal emission that increases in temperature and starts to become present in the soft X-ray band, and of course has other effects on the shape of the spectrum. And this will have clear implications for the nature of the inner thermal disk properties and how the spectrum appears, but also in the timing. So Guglielmo will talk on Wednesday about the impact of this on reverberation lags, for example.
3 minutes left, Barry.
Yep, thank you. So we took high density reflection models, and again, perform the same sort of process. So try to track what the accretion flow properties of this other source, 4U1630, look like as we go from the hard to soft state transition. And in this case, in the soft state, we actually had some new star and swift coverage, a few observations during the soft state, so improved spectral resolution, of course, to try and constrain things such as returning radiation as well. And so I just want to focus on this. One result that came out of this, or one thing I think is interesting, is that when applying reflection models that have this capability of going to higher density, you're now moving into a regime that's slightly more realistic for black hole binaries. And you should be able to check that the ionization constraints you're getting from fitting to the data makes sense. So on the left-hand figure here, I'm showing with red points, the ionization constraints, which is a parameter of reflection models from fitting to the data, and a comparison there with in the shaded regions of what we expect the ionization as seen by the observer should be, given that we have a fit to the data where we have a constraint on, in this case, assuming a lamppost geometry, we have a constraint on the height of the corona, and we can therefore calculate what the flux is striking the disk within some uncertainties, as well as the uncertainties on the density from fitting to the data. And here we find that we have a pretty good consistency. So even if the disk is very close to the innermost stable circular orbit, we know that we're not in this regime where we're shining far too much flux on the inner part of the accretion disk. And I think this is quite key to stress, that if we're applying these high density reflection models to these sources, we should be checking for a consistency in the scales. And finally, in modeling of the Swift and NuStar data that we had available to us in the soft state, similar to what I showed before, we tried to look at, well, what's the reflection spectrum looking like there? Is it more power law-like or black body-like? And it turns out, again, a black body-like reflection model fits to the data much more simply and makes more sense energetically in terms of the coronal component dominating at higher energies and a subdominant Compton hub. So again, here we think we could be seeing returning radiation. I just wanted to briefly give a mention. Jeroen, of course, talked a lot about all the cool results that have come out of NICER of late. This is another source that was detected by NICER. It's not a new source. It was last in Outburst in 2002, but it's the brightest black hole transient observed by NICER to date. It reached 9 crab during its peak, and we have simultaneous NICER and NuSTAR coverage of this source in a very, very bright soft state. So this will be really cool for us to try and see if this returning radiation idea makes any sense here with much improved data. So just to summarize, there's 2 things I've really discussed here, albeit relatively quickly, but that we think in the soft state of these sources, we might be seeing what's called returning radiation. So the reflection spectrum could originate from photons that are bent back towards the disk, so thermal disk photons that strike the disk and create reflection features. Please see Thomas Dowser's talk tomorrow on this, because there's a lot of implications regarding just the second order reflection component as well, and what that changes in terms of the constraints we're going to get from reflection modeling. And finally, that consistent reflection modeling in black hole binaries definitely requires us to go to these higher densities, and there's been several papers exploring that in recent years. But when we do this, we should be checking that the scales make sense, that the radiating flux that we're seeing on the disk and the density constraints we have mean that the ionization is realistic and not just far exceeding that value, because that would tell us something about the geometry that we're getting when fitting to the data and whether it's realistic. Thank you, and please ask questions if you have any.
Thanks, Riley, for the nice talk. Questions, please.
I have one question. Right.
Okay.
Yeah. So in this last slide, so the age of the X-ray source is coming from the fit of your X-ray data, right? Or is it constrained?
Yes.
So it is the same when the disk is truncated or not when you did the fit?
No. Okay. So the heights that I got from fitting to the data all assumed that the disk was at the ISCO. Then I didn't refit and change the inner radius and then get a new constraint on the height. I simply decided to see, okay, what would the ionization look like if I just truncate the disk a little bit? So it's the same heights.
Okay, but then it's no more consistent with the fit. This is the point. So, for example, if you want to agree with the data, perhaps you will have to play with the height of the source if it is truncated, right? Or
yeah, but it's also about limits, right? So as I truncate the disk, it's, if I lower the height slightly, the heights that we got from these fits are already pretty low, on the order of a few to 10 RG. So slightly lowering that for a truncated disk, actually the optimal combination will be something where the height and the radius are at similar values. But it's about limits. So if I push the disk a little bit further out, regardless of where I move the height, we're unlikely to get predicted ionizations that go much higher. They're usually just going to drop.
Okay. Thank you.
Thank you, Victoria.
Hi, I should know that, but I realized I don't, and I'm not sure whether this is the best question to you or to Thomas. But I assume that returning radiation would also have a timing signature, right? So can we constrain that with current instruments, or is this something, should we search for that with the current instruments, or is this something for the future? And well, am I correct with that, with the assumption?
Yeah, so okay, in actual fact, so I'm talking here, I guess, about just the black body component returning to the disk and being reflected. But Dan Wilkins' paper, for example, last year, and what Thomas Dowser will discuss in his talk, is really focused on the coronal emission striking the disk and then being reflected again, so returning to the disk and being reflected again. And I may get this wrong, but I think that this will cause an increase in the reverberation lags, for example, just that effect in itself. In the case of the soft emission returning to the disk and being reflected, I'm not sure. I guess asking Thomas would be better. But in the case of including this effect, in terms of second order reflection, it does have implications for the lag that you expect to see.
Thank you.
Yeah, there is one question here in the room if there is time for that.
Sure.
Yeah.
Hi, this is Andrzej Zdziarski. I just wanted to comment about this issue of high density, that if you assume constant ionization, then if you increase density 1,000 times, you also increase flux 1,000 times. So, so the effect shown by you from the paper by Javier are mostly due to moving the effective temperature of the reprocessed radiation to higher energies. You could study the effect of density if you just fix the irradiating flux and change density. And the usual explanation in published paper is that, oh, this is just the effect of increasing of atomic physics in the reflecting medium, but or more absorption or more emission. But in fact, this is simple effect of changing the irradiating flux. So what is your opinion on that?
I'm not sure I understood the last part of what you said, but yeah, I'm familiar with your paper addressing this. And I think the reason why, for example, I'm showing this calculation that can be done to simply try and constrain, of course, the ionization of the disk is not constant with radius. This is an assumption that's incorrect, but as a baseline level, trying to check that the ionization of the inner accretion disk, for example, matches that you'd expect for your given geometry is one way of checking this idea without too much uncertainty. I think once you move into trying to predict, for example, what the temperature of the reprocessed component should be, there's a lot of uncertainty there. There are, energy shifts in the photons and a redistribution of the energy in both the illuminating continuum and the continuum that will come out of that. So these models are quite complex, right? So there's a lot of things happening when the upper layer is irradiated, and then as this emission is returning outwards and being reprocessed. There's too much uncertainty there, in my opinion, for you to estimate very clearly what the emerging temperature of that quasi-thermal component will be.
Okay, maybe we can discuss it later, but I think it's not so much uncertainty, but okay.